Hi everyone, welcome back to my YouTube videos. So to illustrate the convergence theory of continuous time Markov chain, in this video and the next ones, I'm going to look at examples of queuing systems. So you remember that we saw already those queuing systems in the previous playlist about Poisson processes. That's those systems where typically you have a server, people waiting in line for service, people arrive at the times of a Poisson process with a given parameter, and the service times are exponentially distributed with some fixed parameter. So using the tools from the theory of Poisson processes, we could answer some simple questions about those type of queuing systems. But now that we know more about continuous time Markov chain, we can use the framework, the more powerful framework of continuous time Markov chain to answer more specific questions about those queuing systems. So in this video, we are going to look at one of the simplest possible queuing system you can imagine, called the MM1 queue, where customers arrive at a constant rate. I'm going to call it alpha, and they leave at another constant rate, mu, that corresponds to the rate at which the server is working. So just to briefly explain the notation, so MM means Markov, and so in this case that means that customers arrive at the times of a Poisson process, and the second M means that also the customers leave at the times of another independent Poisson process, so which makes the whole system indeed a continuous time Markov chain. So that's to explain those two M's here. The one at the end refers to the number of servers. In this video, I'm looking at the case of only one server. In the next videos, I'm going to look again at this MM1 queue, but with some variation where customers arrive at different rates, or they can also decide to leave the line without waiting for service. But after, we are also going to study like queuing system where there are multiple servers, so either a finite number of servers or infinitely many servers, in which case the time customers have to wait is 0, so you have immediate service. And so in this video and also over like the next one, so we can answer more sophisticated questions about those type of systems using the framework of continuous time Markov chain. And in particular, one of the main questions is to study the stability of the system, so meaning whether the total number of customers in the system is going to converge to a stationary distribution, or if the system is transient or non-recurrent, in which case we don't have convergence to a stationary distribution. We can also answer questions like what is the expected number of customers in the system at equilibrium, or what is the expected amount of time a new arrival, a customer arriving is going to wait at equilibrium. So in this case, that's exactly the two questions we want to answer for this MM1 queue, with arrival at rate alpha, departure at rate mu. Question one, we want to study the stability of this queuing system. So meaning study the existence and uniqueness of a stationary distribution, and then in case indeed the system is stable, we want to find the expected amount of time a customer is going to spend waiting in line. So I'm going to just draw a little picture here again to just show you that the system looks like that. So you have customer waiting here, customer is going to leave at rate mu, you have other customers in line like this, and new arrivals are at rate alpha. So the first thing to observe about all those queuing systems is that you cannot have simultaneous arrivals or simultaneous departures. So which means that if you call xt the number of people in the system, or you can also call xt the number of people in line, waiting in line, then xt is a process that can only jump from an integer to the previous one or the next one. So that means that in particular, xt, the total number of people in the system, is going to be a birth and death process. And we already know about necessary and sufficient condition for positive recurrence of those very general birth and death processes. And so that's what I'm going to use here to study whether this system is stable or not. So in fact, you don't even need to write an equation to at least guess what's going to happen. It's clear that if alpha is larger than mu, then the number of people in the system is going to tend to increase, and that's when the number of people in the system is going to go up to infinity, in which case this process is going to be transient. Now you have some kind of critical behavior when alpha equals mu. In this case, people entering, people leaving, that's two things happening at the same rate. In this case, it's easy to see that the total number of people in the system is going to behave like a symmetric random walk, with this condition that the random walk cannot go below zero. So in this case, the system is recurrent, but it's not going to be positive recurrent, so it's not going to be stable either. At the opposite, if alpha is less than mu, then meaning the server works fast enough to take care of customers, like at least faster than the rate at which customers arrive. And so in this case, we expect that the expected amount of time it's going to take to have the number of customers in the system going to zero, it's going to be finite in expected value. And so in this case, the system should be positive recurrent. So that's the intuition. In fact, we can prove that rigorously. So you remember that from a previous video that I did about birth and death processes, we know that if there is a stationary distribution, so this stationary distribution pi should satisfy pi x. And here I didn't write, but implicitly I'm assuming that the continuous time Markov chain we are dealing with in the background, it's xt that keeps track of the number of customers in the system. So pi x is going to be equal to beta 0 times beta 1 and so on up to beta x minus 1 divided by delta 1. So you remember we shift a little bit here, delta 2, and we go up to delta x pi 0. So those betas, they represent the birth parameters of our birth and death process. The deltas are the death parameters. In this case, things are very easy because you see that the birth parameter, so the rate at which there is someone arriving, does not depend on x. So all those beta I, they are in fact equal to alpha. All the delta I are equal to mu. And so eventually this simplifies and that gives you some alpha over mu at the power x times pi 0. Now it's clear that if alpha is larger than mu, when this quantity here goes up to infinity, so that means that there are indeed stationary measures, but we don't have any stationary distribution, so the system is not stable. Then at the opposite, if alpha is strictly less than mu, then this quantity goes to zero exponentially fast, in which case, indeed, there is a stationary distribution. The case alpha equals mu is some kind of critical case where you see that pi x is equal to pi 0 for all x. And in this case, again, because the state space is infinite, that means that there is no stationary distribution. In this case, you can prove that the process is recurrent, but not positive recurrent, so it's null recurrent. So now how can we, so based on that, now we are going to assume that alpha is less than mu, so that answers in part the first question, the fact that the process is stable if and only if alpha is less than mu, strictly less than mu. Now we can go a little bit further and compute explicitly the stationary distribution. So we have this relationship between pi x and pi 0. Now the only last thing we need to do is to find pi 0. So for which values of pi 0, how should we choose pi 0 such that the sum of the coordinate is equal to 1? So you see that we must have that 1 equals infinite sum for x equals 0 to infinity of pi x. Now I'm just going to replace pi x by its value, so that means that we have the sum for x equals 0 to infinity of alpha over mu at the power x times pi 0. So this should be equal to 1. Clearly, the infinite sum, so when, of course, alpha is less than mu, is going to converge to 1 divided by 1 minus alpha over mu. And so eventually we get that this is pi 0 divided by 1 minus alpha over mu. And so eventually we conclude that, so because this must be equal to 1, we conclude that pi 0 is equal to 1 minus alpha over mu. And so from that, so we don't need this anymore. From that we can conclude, so we remember that pi x is equal to the alpha over mu at the power x times pi 0. So we get eventually pi x in the case where alpha is less than mu, so is equal to, we said alpha over mu at the power x times pi 0, but pi 0 is given by this expression, so 1 minus alpha over mu, and that's it. So that gives you an explicit expression of the stationary distribution. And so the way to understand that number is really to say that if you let the process evolve long enough so that it reaches equilibrium, then the probability of having X customers, that you see X customers in the system is going to be this. So that's the probability of X customers in the system. So now it turns out that pi has a name here. You see that's of the form 1 minus p at the power x times p, where p is equal to this parameter. That's exactly a geometric random variable, except that for a geometric random variable, we will need a x minus 1 here. That's x minus 1 failures, then 1 success. But of course here the number of people in the system cannot be a geometric random variable because it's possible that there is nobody in the system, but the geometric random variable starts from 1. So instead this one is in fact the shifted geometric random variable with parameter 1 minus alpha over mu. So that's exactly the same as the geometric random variable, but minus 1. So I'm going to write this also here. This means exactly that pi is shifted geometric, so I'm just going to write geometric. The parameter is this, 1 minus alpha over mu, but this thing minus 1. Okay? So now we fully answered question 1. Now let's look at question 2. Question 2 is what is the expected amount of time a customer is going to wait in line, so not be in the system, but wait in line at equilibrium. So we assume that the system is at equilibrium and we want to find the expected value of this time. I'm going to write this time t, and so we want to find expected value of t. I'm going to write a pi here, where pi is exactly this one, this shifted geometric. That means what is the expected amount of time a customer is going to wait in line, but if the system is distributed according to the stationary distribution, pi. So in this case, it's clear that the time a customer will have to wait clearly depends on the number of customers in front of this person, okay? So that depends on how many customers are already in the system when this customer arrives. And so, but we know the probability of X customers in general. So the idea to compute this expected value is to condition on, let's say, xt, number of people in the system. So we condition on xt, but we have also in mind that we are at equilibrium. So in fact, you can rewrite this and say that this is the expected value pi of the conditional expectation of t given xt. I'm writing xt here, but in fact, t does not matter because we assume that the process is at equilibrium, so that's going to be distributed according to pi at any according to pi at any time t. So then, of course, this is equal to the sum for all the possible values of xt. So that's going to be x equals 0 to infinity. So 0 here it's going to be, so this xt is really the number of customers in the system just before the customer we are looking at is coming in the system. So it's clear that so now I'm looking at expected value of t given that xt equals s times x times the probability that xt equals x. So the expected value of t given that you have x customers in the system is going to be, so x customer in the system is going to be, so you have 1, 2, 3 up to x, let's say, and so in this case this customer arriving here, this new customer arriving, will have to wait in average 1 over mu for this one to leave, and another 1 over mu for this one to leave, and so on. So the average is clearly x over mu. So if you know that there are x people in front of you, and you count the person in service, so if there are x people in front of you, the time you will have to wait in average is x over mu. So that tells you the value of expected value of t given that xt equals x. So this one is, we said x over mu. Then you still need to multiply by the probability that xt equals little x. Of course, that's under the stationary distribution. So this one, by definition, is just pi x. So that's just pi x. But then this tells you that the sum is just 1 over mu times infinite sum of x pi x. That's the expected value. By definition, that's the expected value of pi. That's the sum of all the x pi x for all x in the range of pi, in the range of this shifted geometric random variable. So eventually you just get 1 over mu times expected value of pi. And now expected value of pi is exactly expected value of a geometric random variable minus this one. I mean, expected value of this geometric only, so it's 1 divided by that minus 1. So eventually you get 1 over mu times, so you have a 1 over 1 minus alpha over mu minus 1. And of course you can simplify that a little bit. So let me keep this result here, and that's the answer to question 1. And let's finish this calculation here. So we proved so far that expected value, so at equilibrium, of the expected amount of time a new arrival is going to wait. So that's this, so you can expand a little bit, so that's going to be a 1 divided by mu minus alpha. So 1 divided by mu minus alpha minus 1 over mu. Let's multiply those two things so we can simplify by saying that it's mu minus alpha divided by the product of those two ones. So that's going to be mu minus alpha times mu. And so eventually you can simplify even a little bit more, and so those mu's, they disappear, and so eventually you get alpha over mu, so alpha over mu times alpha over mu times 1 divided by mu minus alpha. So you see that here, of course, we assume that alpha is less than mu. So indeed, this mu minus alpha is strictly positive. So eventually, conclusion to the two questions, if I recap. So the system is stable if and only if alpha is less than mu, in which case at equilibrium, the number of customers in the system is distributed according to a shifted geometric random variable with formula 1 minus alpha over mu, and the expected amount of time each new arrival will have to wait is equal to alpha over mu times 1 divided by mu minus alpha.